So, hello and welcome to lesson 6 in our study of mathematical biology 2. So, in this lesson, we'll be talking about the competition model. We started learning population dynamics, right? Models for describing population dynamics in species. We talked about when we have just a single population, and we talked about the Malthusian model, the logistic model, and we also learned about harvesting in population model. Then we started learning the population dynamics of interacting species. Okay, so we talked about the predator prey model, and today we're talking about the competition model. Okay, so let's take some intro. So it says in our previous video we talked about the predator prey model where one species benefits whilst the other doesn't. In this video we'll talk about the model for describing when two species compete for same food resources. Okay, so two or more species may compete for the same limited food source or some way inhibit each other's growth. And what this statement means is that because they are competing for the same limited food resource, the growth of one will somehow depend on the other, because in the absence of one, the food that one will get will be reduced when the two of them are together. Okay, so for example, competition may be for territory, which is directly related to food resources. So we are going to consider a work by Hu and al. Right? But in 1979, who discussed that when two species compete for the same limited resources, one of the species usually becomes extinct. So that's a two-species Lotka-Volterra competition model with each species X and Y having logistic growth in the absence of the other, right? So if you could recall, when we were talking about the predator prey model, in the absence of the other, each of the species had what Malthusian growth model. But in the case of our competition model, we are going to use the logistic over the Malthusian. Okay. So the inclusion of the logistic growth in the Lotka-Volterra system makes it more realistic than the Malthusian model. So the model is given by what you can see here. And this model is somewhat like the predator prey model that we derived in lesson 5. So let's take that here and let's see how we get that. We got the competition model from it, right? So if you could recall, this was the predator prey model. So you realize that in the absence of, so this is for the predators, this is for the prey, this is for the predators. So in the absence of the predators, this is out. So this is just the growth of the prey, which is the Malthusian, right? And this was also for the depth for the predators, right? Which was the Malthusian. So we had a negative sign here because in the absence of the prey, the predators are going to die, right? So you can see here too, in the absence of what species X, species Y, the growth of species X will just be given by this, which is of the what logistic growth model. We have the SDT will be equal to Rx 1 minus x over k. I hope you can say that here, right? And when they interact, right, um their population are going to reduce because let's say we had two animals competing for the same food resources. So and they are grazing on this land, right? So we have a goat and we have a sheep. So let's say in the absence of sheep, the goats are going to have the whole of this land to graze on. So that means that they are going to grow more, right? In the absence of the goats, so the sheep will have all this to themselves, so they will grow more. But in the presence of both of them, they will have to share this. So that means that they are going to inhibit each other's growth. So that's the reason you can see the minus here and the minus here. So this model here is what we call the competition model, right? So the parameters r1, k1, r2, k2, b1 and b2 are positive parameters, so we have 6 of them. And the r1 and r2 are linear birth rates of species x and y respectively. So k1 and k2 are the carrying capacities of x and y respectively, and b1 and b2 measure the competitive effect of y on x and x on y respectively. So note, they are generally not equal. Okay, so now we have our competition model, right? And we said is this, we derive it from the predator prey model, which made it so simple, right? So before we perform any analysis on the model, we would want to first non-dimensionalize the system. Okay, so this is the model. It has 6 parameters, and mostly performing analysis with these 6 parameters is going to be a bit tedious, and so we would want to reduce the number of parameters, right? So we have to scale and non-dimensionalize. Okay, so we are going to do that. So we are going to use these equations to help us with the non-dimensionalization. Okay, so we are going to define a new dependent variable u1 in terms of the old x, right? So we'll say let u1 be equal to s of t over k1, u2 be equal to y of t over k2. So please take note of these equations because they are the ones you are going to use to do our non-dimensionalization. Okay, so you can see that we take the first equation, we have one dependent variable which is x, but we want to change this to what u. That's the reason we are saying u1. That's why we are saying u1 is equal to x over k1. So we have to use a chain rule. So this is going to be the chain rule for the equation 1. So we have the x dt will be equal to the x, then the new dependent variable du1 times du1 over the new independent variable the tau times the tau over the t. Okay, so we want to change this to this. So that means we have to find the x du1 and we have to find the tau dt. But from the equation that we had here, right? So note, we are going to make use of them a lot. So we will always be making reference from here. So from those equations, we had u1 is equal to x over k1. When you make x the subject, you get x will be equal to u1 k1. So when we find the x du1, we just get k1. And we had tau to be equal to r1t, right? So when we find the tau dt, we get r1. So after getting this, we'll make substitution back in here, and that will give us the x dt will be equal to k1 r1 du1 d tau, and we call this equation a. So we are going to now put this equation a into equation 1, right? So putting equation a into equation 1, wherever we find the x dt, we'll put this there. Wherever we find x, we will put u1 k1 there because s equals u1 k1, and whenever we find y, we'll put u2 k2 there because from here y is equal to u2 times k2. Okay, so that's what we're going to do. So doing that, we'll get k1 r1 will be equal to the u1 d tau, which will be equal to r1 u1 k1 times 1 minus u1 k1 over k1 minus r1 b1 k1 u1 k1 u2 k2. So you see this k1 r1 will cancel through, right? Okay, so after that we can still do more simplification. All right, this k1 will cancel this k1, so now we'll be left with the u1 the tau will be equal to u1 multiplying 1 minus u1, then minus b1 k2 over k1 u1 u2. Okay, but from the equation, yeah, so you can go back and um I told you we'll be making reference of them a lot. We said a1 is equal to b1 k2 over k1, right? So that means a1 is equal to b1 k2 over k1. So the whole of this is now a1. So making that substitution, you're going to get du1 the tau will be equal to u1 minus u1 squared minus a1 u1 u2. And when we have a common factor, which is u1, when we factorize that one out, we get the u1 detail will be equal to u1, or multiplying 1 minus u1 minus a1 u2, right? And this is the non-dimensionalized equation for equation 1. So we have to do the same thing for equation 2, right? This is equation 2. So we have to write a chain rule for equation 2. So the old dependent, you don't understand how we are doing the non-dimensionalization, please, I'll advise you to go and watch the video on lesson 4 when we treated how to non-dimensionalize equations, okay? So here the old parameter is y. We want to define a new one, it in terms of a new one called what, u2. So we are using this relation here. So writing a chain rule for equation 2, we would have dy dt will be equal to dy du2 times the u2 d tau times the tau dt. So we would have to find dy du2, right? So from u2 equals y over k2, y will be equal to u2 k2, and tau is r1t from the equations we defined above. So when you find dy du2, we get k2, and the tau dt will give us r1. So when we make substitution here, we are going to get dy dt will be equal to k2 r1 du2 d tau, okay? Then we take this and we substitute it into equation 2, right? That's the main model for the predator premodel, the species 2, right? So that means that instead of dy dt, you write k2 r1 du2 d tau will be equal to, so wherever you find x, we will put k1 u1. Wherever you find y, you put k2 u2. So doing that, we'll have r1 du2 d tau will be equal to r2 u2. We get k2 r1, sorry, so we get this line. K2 r1 will be equal to du2 d tau, which will be equal to r2 k2 u2. All multiplying 1 minus k2 u2 by k2 minus everything that you have here, okay? So k2 is common, so they will cancel out. Then this k2 will cancel this k2. So we are then going to end up with what you can see here. So when you get here, we said that a2 is equal to b2 k1 over k2. So you can check from the equation that we defined above. So that means the whole of this now becomes a2. So when you put that into the equation, we get this. Then we can decide to divide through by r1. So doing that, we get the u2 d tau will be equal to r2 over r1 u2, whatever you can see here, okay? But we said that rho should be equal to r2 over r1. So making substitution, we'll get the u2 d tau will be equal to rho u2 multiplying 1 minus u2, then minus rho a2 u1 u2. So when we multiply through, we are going to get this, and you can see that they all have a common factor, right, which is rho u2. So when you factorize that out, you are going to get this here, and this here happens to be the non-dimensionalized equation for the second equation, okay? So now that we have our non-dimensionalized system, right, then now we can decide to analyze the system, okay? So we are going to use a fixed point analysis, okay? So we are going to look for fixed points and discuss their stability. So now let's find a fixed point of the system. So to find a fixed point of the system, we put the u1 d tau and the u2 d tau to 0, right? So when we do that, we will get this, we are calling it equation 1, we get this, we are calling it equation 2. And we have to solve equation 1 and equation 2 simultaneously to get values for u1 and values for u2, okay? So from equation 1, we can have u1 to be equal to 0, or whatever we have here to be equal to 0. And that's what you can see here. So that means u1 is equal to 0, right? And from equation 2, we can have rho u2 equals 0, or whatever we have here equals 0. And rho u2 equals 0 implies that u2 is 0, because real is never 0. If real is 0, that means everything that we have here will be 0. So we have u1 to be 0 here and u2 to be 0 here. So, and we also have this second equation. So what we do is that we go to when u2 is 0 and we put it in equation 1. So when u2 is 0 in equation 1, we will get, so this is equation 1, right? So when u2 is 0, we will get 1 minus u1 minus a2 times 0 equals 0. 1 minus u1 will be equal to 0 and u1 will be equal to 1. So when u2 is 0, we get u1 to be 0. So that gives us the point 1, 0. And when u1 is 0 from equation 2, right? So from equation 2 here, when u1 is 0 from equation 1 here, when you put that in equation 2, we get 1 minus u2 equals 0 and u2 is 1. So we also get a point 0, 1. And note that we had u1 to be 0 and u2 to be 0. So that also gives us another fixed point 0, 0. So now, just now we have 3 fixed points. But we have 4 fixed points for this system. Okay. So that's why I say note that u1 star, u2 star equals 0, 0 is also a fixed point. So the last fixed point, that is the non-zero fixed point, is formed by solving these equations, right? So you could see that here we had u1 equals 0 or this, u2 equals 0 or this. So we solve these two equations simultaneously for values for u1 and u2. So we call the first part equation A, we call the second part equation B. So we have to solve it simultaneously, right? So we are deciding to make u1 a subject in equation A and then substitute it in equation B. So doing that is going to give us u1 equals 1 minus e1 u2. Then we put it inside equation B. So wherever you find u1, we put this there. And making that substitution will give us 1 minus u2 minus a2 multiplying 1 minus a1 u2 equals 0. And when you expand that, you get this. When you decide to send all the terms containing u2 to one side, you get this. You factorize u2 out, you have this. You divide through by the coefficient of u2, and that gives you this. So that means this is u2, right? But we know that u1 is equal to 1 minus e1 u2, right? So when we put in the values for u2, we had this. When we expand, we have this, right? We continue expanding, we have this. So trying to work it out is very simple. And finally, we have u1 to be this, right? So that means that the last fixed point, that's the non-zero fixed point, is u1 star a2 star equals 1 minus e1 over 1 minus e1 a2, then comma 1 minus e2 over 1 minus e1 a2 for all e1 a2 not equal to 1, because when a1 times a2 is 1, then that means that all of them are going to be divided by 0, and we will not get a real number, right? We get an undefined fixed point. So hence we have these 4 fixed points, right? And with the fixed point analysis, after getting our fixed points, we would want to discuss their stability. So in this video, we are going to discuss the stability of the first 3 and leave the last one out, because with that one we'd have to do a tedious algebra work before we can get a result on that. Okay, so now discussing the stability of the fixed point. So the system we had, that's a non-dimensionalized system, was this, if you remember, right? So we will let f of u1 u2 be equal to whatever we have here, and let g of u1 u2 also be equal to whatever we have here. So that's why you can see f of u1 u2 is this, which we have expanded to get this, and g of u1 u2 is this, which we have expanded to get this. Okay, so we have to form our Jacobian, right? And the Jacobian will be given by what we can see here. So now we have to find del f1 del u1, del f2 del u2, del f del u2, del g del u1, and del g del u2. So finding them is going to give you this. Okay, so you can try and verify it's correct. So when we make substitution into the Jacobian that we have here, we are going to have this, right? So the next is for us to put our fixed point in. So at the first fixed point, that's u star 1, u star, u1 star, u2 star equals 0, 0. When you put 0, 0, like u1 to be 0 and u2 to be 0 here, we would have this. You get 1, 0, 0, real, right? And finding the fixed point of this Jacobian, you realize that the fixed point to be 1 and real. You realize that 1 is positive and rho is also a positive parameter. Okay, so it means that the fixed point 0, 0 is unstable. Okay, it's unstable. So that means that when we have a few, very, very, very few of the two species, alright, the system will be unstable because they are going to grow exponentially. Okay. Then now let's go to the second fixed point. That's u star, u1 star, u2 star equals 1, 0. So when you put 1, 0 here, right? So that means u1 is 1, so you put 1 there. U2 is 0, you put 0 there. We are going to get this system here, right? And when you find the fixed point, you will get um, lambda 1 to be minus 1 and lambda 2 to be real multiplying 1 minus a2. So you realize that this is negative, right? And for the fixed point to be asymptotically stable, both of them should be negative. And the only case when this will be negative is when a2 is greater than 1. So, but when a2 is less than 1, here will be positive, and that will make the system unstable. So that's why you are saying that u1 star u2 star equals 1, 0 is asymptotically stable if a2 is greater than 1, and it's unstable if a2 is less than 1. Okay, so that's for the second fixed point. So for the third fixed point, 0, 1, when we make substitution into here, right? So that is u1 is 0 and u2 is 1. When you make substitution here, then we are going to get this system here. When you find for the fixed point, you are going to get lambda 1 to be 1 minus a1 and lambda 2 to be minus 0. So that means that for, this is always negative, right? For this to also be negative, a1 should be greater than 1. Then we will have the system to be the fixed point to be asymptotically stable. If not, if a1 is less than 1, then it will be what? Unstable, right? So know that here we're interested in when it is stable and when it is not. Okay, so we said we're going to discuss the stability of the three fixed points and leave that of the non-zero fixed point out. Okay, so the reason why I'm leaving it out is because we have to do tedious algebra, which we are not ready to do in this video. So at the non-zero fixed points, this is what we had, right? And this was our Jacobian matrix. So that means that wherever we have u1, we put this there. Wherever we have u2, we are going to put this there. And see the system we are going to get. We are going to get this matrix here, right? And when we make simplification, we'll get this. And after that, we have to find the eigenvalues of this system. That's going to give us something like this, right? And when we decide to expand, we are going to get something like this. And this can be solved though, it can be simplified though, but it can be simplified by tedious algebra techniques, right? And for the purpose of this video, we wanted to discuss the stability of the fixed point, the 0, 0, 1, 0, and 0, 1. So maybe later on you would want to continue with this, but for the purpose of this video, this way we end. Okay, so that's a competition model for you and how you can analyze it a bit. Okay, so thank you very much and see you in the next lesson.